All right, hello everybody. We are live. In this segment, we are going to go through a little bit of a case study here using the sales.csv data set and implementing some multiple linear regression. We'll look at some, building different models, thinking about model assessment, and then at the end we will kind of go through an idea of partitioning the data into a training set and a test set or a validation set. And we will look at getting a better estimate of our out-of-sample prediction error. We're going to start off by importing the data. So this data is at my GitHub account. There is a column header. First row of the data actually are the column header information. So I'm going to set that header argument here equal to true. So that is what that is doing. Header equals true means if you have column headers in your data, then you want to not have that particular row treated like your first observation. And I'm going to just go ahead and run that particular line there. Let's go ahead and run line 12. And you'll notice right away in my global environment, it says here we have a data frame. Notice I stored this in a variable called df for data frame. This is a name that I just picked here. So df is the data frame. That is the name of the data set now that we've imported here. And we can see over in the top right that we have 365 observations on 8 variables. It's actually 1 year of daily data, and actually some time series data here that we'll look at in a moment. But let's go ahead and do a little bit of exploratory analysis so we can make sure we're familiarized with the structure of that data set. Recall the DIM function. This allows us to view the dimensionality of the data set. If we run that, it will tell us as the first argument the number of rows or observations, which is 365, which matched what we saw in our global environment. We also see here that the number of columns in the data set are 8. So there are 8 variables. If we run the head function, this will show us just a summary of the first 6 observations in the data set down here in our console window. So that is what we are looking at down here. Just the first 6 observations gives us a little bit of summary structure of that data set. So we can see here, we have 8 variables, but 1, 2, 3 of them are pretty much date related variables. We have this other variable promo, which tells us whether or not a website wide promotion was run on a given day. 0 for that day means it was not run. 1 means it was. So we can see here, on Saturday, January 6th, they did run a promotion. We have the quantity of sales on the given day, the price charged for the good on that given day, the amount of targeted ad spending associated with those unit sales on a given day. And in this last column here is the number of social media impressions that had converted to these sales on a given day. We could also view the entire spreadsheet of data if we wanted to. And this is okay if you have few observations, but if you have millions of observations, I wouldn't recommend this. But this is the view function with a capital V. You'll notice we run that. We can actually look at the entire spreadsheet here, all these observations for all these variables. You can scroll. That's useful if you want to get, again, a general idea of the structure without running the head function or the tail function, which would show you the last 6 observations. Other descriptive metrics that are important to look at here are some summary statistics. We'll look at the 6-number summary for each variable by running summary on the entire data frame here in line 23. Let's go ahead and do that. And we can see down in the console window, we have summary data, at least for each of the quantitative variables. Sales, we can see here, we got our min, first quartile, median, which is the second quartile. We also have the mean, third quartile, and the max. So it gives us some idea of how our data are distributed here. We can see the mean promo is about 10. And what that means actually is if we added up all the days divided by the total number of days, we would be adding up a bunch of zeros and ones for that promo variable. So that mean of 9.863% tells us there was a promotion run on roughly 10% of the days, but we'll come back to that. You'll notice for the other date variables, these are not quantitative, they are qualitative. So it's giving us some summary of the different classes in each case and the number of occurrences, right? We see here Friday occurs 52 times in this data set. And that makes sense. There's 52 weeks in the year in general. You'll notice Monday occurs in extra time. And you can think about why that's the case for any particular year. The other thing that's important to look at, not just this general summary of how these variables are distributed here. Note we can look at things like the mean and the median, and we can see, for example, that promo variable, the mean and the median are fairly different. And that's pretty good evidence that we're dealing with some skewness here in that particular variable without explicitly computing a skewness metric. So we're getting some idea of the structure of the overall data set. Let's go ahead and look at some relationships between variables. So what we're going to do here is we're going to generate a variance covariance matrix, okay, which will show us the covariance between different variables in the data set, as well as the variance, which is the covariance of a variable with itself. And we're going to do this for what we're saying here is for specifically columns 5 through 8. Okay, so you'll note this 5:8, that is the column number. You'll see here to the left of the comma, we did not put a row number in there. And what that's going to do is it's going to tell R to pull all the rows. Okay, so we're going to use all the observations, all 365 observations. And we're only going to pull columns 5 through 8. And if we jump back to our spreadsheet view of the data frame here, we can make sure we see what columns 5 through 8 specifically are here. So column 5 is sales, 6, 7, and 8 are price, ad spend, and impression. So we're going to go ahead and look at the relationship or association between those variables. And we're going to take two perspectives. We'll look first at the variance covariance matrix. Okay, and we can see that is generated now down in the console window here. It is the variance covariance matrix from running line 24 up here. And we can note a few things. Okay, there's a few important things to notice here in terms of the strength of relationships with signs. We see that there are some things that look like they have negative covariances, right? This says we have negative covariance between price and sales, and I think that makes sense given what we know about the law of demand from economics, right? Higher the price, lower sales, they should be inversely related. We also see a negative relationship here between price and ad spend, but again, the covariance, the units of measurement are somewhat distorted by the units of measurement of each of the variables that we're taking the covariance between. And it also looks like we have a negative relationship between impressions and the price. And you'll notice there are some off-diagonal entries which are the same as their corresponding one, right? That negative 864, we see that value again right over here. Those two are related, right? We also see this negative 33 value show up again. That was right there, right? Negative 83.815 right here. So you only need really the half of this matrix to really start looking at relationships between things. But we have some idea where are positive relationships, where are negative relationships. And just one more note about this matrix. If you look at the diagonal values specifically of the variance covariance matrix, well, this value here is the covariance of sales with itself, which is the variance of sales. This is the variance of the price variable, variance of ad spend, and variance of impressions. Now, unfortunately, covariance measures we know are distorted by the units of measurement of the underlying data. So what we're going to do next is we're actually going to generate a similar type of matrix. We're going to generate here the correlation matrix for the same set of variables. And we will be able to compare the two. And we'll notice when we do this, when we generate the correlation matrix, okay, we're still capturing the same sign of relationships, right? We see here, we have that negative covariance between price and sales. And we see that is preserved when we look down at the correlation, right? But we also see there's a lot of positive correlations, some pretty strong positive correlations, in fact. Let's look at those. We see sales and ad spend has a pretty strong correlation, 0.73. Okay, so we'll maybe think about building a model that looks at that relationship in a little bit. But the correlation matrix, these are unit-free measures. The correlation's got to be between -1 and +1. -1 being indicative of a perfect negative linear relationship, and +1 being indicative of a perfect positive relationship. Your data falls literally on the same line. So we're kind of getting some idea here by looking at the correlation matrix and thinking about, how are variables related, and maybe we can start testing some of these relationships. You'll notice the relationship between sales and price, despite the fact it's negative, it is pretty small. So we might want to think about building a regression model and testing whether or not that's a significant relationship for us to be thinking about. But certainly here, the relationship between ad spend and sales, surely that is probably significant. But again, we can think about building a regression model and testing that. So moving on, let's go ahead and take a look at the distribution of the sales variable here. So we're going to build a histogram using this histogram function. And you'll notice I'm feeding in an argument here. It says probability equals true. And what that's going to do is, instead of measuring the count on the vertical axis, it's going to measure the relative frequency. It's going to measure a probability on the vertical axis of the histogram. So let's go ahead and run line 28 here and take a look at the output in the bottom right plot window. Okay, so what we're plotting here is a histogram using the data frame with the sales variable. So we use this $ here. Okay, that $ that allows us to grab the sales variable, okay, from that data frame. And we're going to go ahead and plot that histogram. So let's run line 28 here. Again, if you want to just run that line, put your cursor on it, you hit Control Enter or Command Enter. And boom, right there in the bottom right corner, you can see immediately we have our histogram for that sales data. Okay, and it looks fairly normally distributed. In fact, if we wanted to, we can overlay a standard normal curve here. So let me just go ahead and pull this window a little to the right so you can see the arguments that I'm passing in line 30. So we're going to use the curve function. We're feeding it the normal density function. Okay, so this d norm, that is the density function for the normal distribution. We're going to set the mean equal to the mean of the sales data so that the normal curve has the same mean as the underlying histogram. We're going to set the standard deviation for the normal distribution equal to the same standard deviation as the data. We'll have it show up in dark blue. The line width will be 2. We can change that number if we want to make it thicker. And add equals true because we're going to add this curve to the current diagram that we have produced here. So let's go ahead and run line 30. And you can see now, once we've done that, in the bottom right panel, it looks like we have a nice overlay of a normal distribution right on top of our empirical distribution, that blocky distribution. That's the actual data. So it looks like sales is somewhat normally distributed. We can actually run a hypothesis test. I'll show you how to do this a little bit later in the video, where we run what's called a Jark-Barrett test. And we can, it's a parametric test that compares the skewness and the kurtosis, the thickness of the tails, to a normal distribution to check whether or not the null hypothesis that the data is normally distributed is reasonable, or if we can reject it in favor of an alternative that the data is not actually normally distributed. We could also plot a density curve, which is a type of non-parametric estimation, which gives us essentially a smooth histogram plot for that data, which looks like this. And another useful feature to look at here is this pairs plot. And what the pairs plot will do is it's going to generate for us a scatter plot. And we're specifically, again, feeding it only the variables from columns 5 through 8. So sales, price, ad spend, and impressions. So if we run this pairs plot, what that's going to do is it's going to generate a matrix of plots that provides us with essentially a visual representation of the information that we had seen down here in this correlation matrix. It's going to provide us a visual representation to be able to look and see whether or not, there are negative relationships between variables when we plot a scatter plot, or if there is a strong positive relationship between variables in the scatter plot. So let's go ahead, increase the size of this. If you don't have this window blown up, you might get a little warning or an error and the plot doesn't run, but just no problem. Make that window bigger, run that pairs function. And you can see here now, we're looking essentially at the same information we had in the correlation matrix here, right? But instead, okay, we have scatter plots. So if we wanted to, for example, look at the relationship between sales and ad spend, which we said looks like it's going to be strong and positive. If we move over to the right set of plots, we can see here the relationship between sales and ad spend is captured in this diagram here, where sales is measured on the vertical axis, ad spend is measured on the horizontal axis. Okay, and it looks like a pretty strong relationship. You'll notice this picture over here on the off diagonal is also the relationship between sales and ad spend, except in the bottom left diagram, sales is measured on the horizontal axis and ad spend is measured on the vertical axis. So again, these pictures in the top right triangle of this scatter plot matrix, they are really the mirror images of the ones in the bottom left. So again, we do see here pretty strong relationship between sales and ad spend. That might be something we want to consider when building a regression model with our data. In fact, there's a couple other types of plots we could generate here. If we wanted to look at, let's say, the time series plot of sales, which is indexed by observation. And again, if we go to the data frame, we can see our observations are really days of the year. We can run the plot function on the sales data, on the DF data set using the sales variable. And we're going to tell it to make it a line graph, type equals L. You can play with that argument as usual. Again, you can use a question mark in front of that plot function to pull up the help documentation to see all the cool different aesthetics that you can control about this function by feeding it different arguments here. Let's go ahead and just run this function so you can see what the sales time series plot looks like. It looks pretty messy. There it is. Okay, so along the horizontal axis here, we are looking at time from day 1 of the year all the way to day 360. And we can see here that the sales looks like they fluctuate. There might be a little bit of seasonality pattern going on in there. Maybe looks like on average, you know, the sales is going up and down, right? Maybe something like that. So we might want to think about testing for seasonality, and I'll show you just kind of an introductory way of thinking about this without getting too much into time series analysis. But we did see in one of a previous plots, let me just go back, I'm gonna hit this back button here to go back to our pairs plot. We did recognize that there was this strong relationship between sales and ad spend. So let's go ahead and zoom in on that relationship by creating a new plot where we only look at that relationship. So the plot function here, the way I'm using it now, the first argument I'm feeding it is the sales variable. That'll be the Y value. The second variable will be the X value. So this is Y tilde X. And there are other ways you can feed it that information to generate the same plot. But this is one way to do it. There is the picture of the plot. Okay, and I think as we suspected, it looks like a fairly strong positive relationship. It had a correlation above positive 0.7, right? Fairly strong there. So let's go ahead and build some linear models using our regression toolkit and see if we can model this particular relationship. So this first model we're going to look at here, we're going to try to capture the relationship that we see in this right scatter plot that we built. So we're going to build a linear model to quantify the relationship between sales and ad spend. So here's the model that we're going to build. Sales is the Y variable. We're going to have an intercept term B0. We're going to have a slope term B1. And the X variable here is ad spend in parentheses. And of course, there is some residual that we'll estimate. So we're going to use the linear model function to do this. This is the LM function. And there are a couple arguments we're feeding it here. First, I'm feeding it the name of the Y variable. And then I have a tilde, which functions as the equal sign. And then we feed it the name of the X variable on the right-hand side. I don't need to say intercept or slope. Don't have to put that in there. Okay, so we basically need to just be able to describe the model to the computer. And of course, I have to tell it which data frame to use, because otherwise it does not know where the sales and the ad spend variables come from. So when we run that particular line of code on line 46, okay, what will happen is in our global environment in the top right, you'll note that we'll see a new object pops up, and that object is a regression model, M1. And it has a list of 12 different characteristics, 12 different features of that model that we can play with. And we're going to just go ahead and use the summary function here to pull up the model diagnostics down in the console window. So let me go ahead and give us a little bit more room here to look, to run the summary function on line 49. And we're going to take a look down in the console window below to look at the results of our output. So down in the console window, okay, we have the output, or the summary output rather, from building our linear regression model here. Okay, and you'll note the form of the model says we had sales as the Y variable and we had ad spend on the right as the X variable. So this here was the function call that we had put in. Okay, you'll notice it gives us some information about how the residuals are distributed. A mean residual of a regression when you have an intercept term and a slope term, always going to be 0, but you'll notice the median is actually not 0. There's a little bit of skewness in the residual distribution. That might be something to think about. But perhaps most importantly, the key thing we want to be able to look at here is this part of the table, which tells us about our coefficient estimates. Okay, and right away, we can see here that we have a coefficient estimate of 1.243 times 10 to the 4th power, okay? Which is 12,000 something. That's the intercept value here in our model. And we also can see the slope parameter on ad spend is 1.885 times 10 to the 1, or about 18.85. And what that suggests is that when ad spend goes up by 1 unit, sales goes up by about 18.85 units on average. The other things to note here are that we also have reported the standard error of each of those beta values, right, for the intercept and the slope. We also have a column that reports the t statistic for the individual significance test, and the far right column gives us the p-value associated with that t-test for each of those terms. So you'll note right away here, we have a near 0 p-value, 1.44 times 10 to the minus 10, right? So that's like a decimal point. You got 9 zeros, and then you get some digits. And we have also a very significant beta 1 coefficient or slope coefficient in the model, which is giving us a p-value, again, close to 0, 2 times 10 to the negative 16th. And that was from us all running the summary function. The other thing to take note of here is the output down here regarding the significance codes. If you see 3 stars next to the p-value, then what this is telling you is you are dealing with a result that is significant between the 0% level and the 0.001. So you got some definitely significantly strong results here. And we can see on the right, we have those 3 stars showing up next to both of our parameter estimates. So they are both individually statistically significant. The other thing we can see here is that there is some joint significance in our model as well, which makes sense. Here is the F statistic associated with the F test. Okay, and note the p-value on that F statistic is also extremely low, 2.2 times 10 to the negative 16. Okay, definitely below the 0.05 standard threshold that we use for measuring significance. So we were able to build the model, we're able to generate our summary output. The other piece of summary output that I would like to direct you to here as well are the multiple R squared. Here's our R squared. What that value there is telling us right now is that about 54% of the fluctuation in sales from day to day are explained by the variations in ad spending. Okay, so our model here is able to explain about 54% of the fluctuation in sales. A couple other important metrics to look at down there as well regarding the goodness of fit of the model. We have our residual standard error, and that's going to be measured in dollars, right? Because our Y value sales is measured in dollars here. We also have the adjusted R squared, which is going to be important to look at when we're comparing models, and we will do that momentarily. So let's go ahead and we're going to run the next line of code here. What this next line does is it actually returns the upper and lower bounds for a 95% confidence interval on these parameter estimates. So remember what our parameter estimates were. This was B0, was that 1.243 times 10 to the 4th. And we had this coefficient on ad spend, which was 1.885 times 10 to the 1st power. And if we run the confident function on M1, What that does here is it gives us a table that shows us the lower and upper bounds on the 95% confidence interval here. So this value 8,728, that is the lower bound on the intercept terms confidence interval. Here is the upper bound on the intercept terms confidence interval. Similarly for the coefficients on ad spend as well. We have a lower bound of 17 and upper bound of 20. And again, the average is about 18.85 in terms of that B1 value that we've estimated here. So pretty easy there to recover, confidence interval. If you had to do that for your project or something, very, very easy. Use that conf function on the model that you've just created, and it will display the confidence intervals for you associated with those parameter estimates. It's also nice to be able to visualize the results. So what we're going to do here, we have our plot of sales and ad spend in the bottom right. You can run that again if you want, but you'll see the same thing. What we're going to do is we're going to add a line to it using the AB line function, and we're going to feed it the coefficients from model 1. Okay, and you'll notice I'm using the square bracket here to tell it to give me the first coefficient, which was the coefficient on the intercept term. Right, that was the first coefficient, B0. The second coefficient we estimated, coefficient 2, that was the coefficient on ad spend. That was our slope coefficient. So we're basically passing this AB line function 2 pieces of information. We're passing it the intercept of the line we want to draw. We're passing it the slope of the line we want to draw. And then again, I'm saying let's color it blue, and we'll have a line width of 2. So when we run line 54 here, what that does is it adds the actual regression line that we estimated to our plot. Okay, and the other thing we could think about doing here is plotting the fitted values of the regression. Okay, so we're going to create a new plot, okay, where we just plot the fitted values. And hopefully you remember the fitted values, they should literally fall right along the regression line. That is what we're doing. We're plugging in the X values in the data along the horizontal axis into that regression line. So when we plot those fitted values, okay, we wind up getting a plot that was right along that regression line right there. Okay, the other thing we may want to do is check our residuals to see if whether or not there are nonlinear effects we haven't captured here and understand the distribution of these residuals. So we could plot the residuals, and it's a little hard to see what's going on here. Let's plot a 0, 0 line, a 0 intercept, 0 slope, just a flat line right across 0. And it's kind of hard to see how the residuals are distributed. It doesn't look like there's a clear pattern of the residuals changing in any way as we move across observations. So we don't really have heteroscedastic error to deal with here. And if we plot a histogram of the residuals, we can see that they do look fairly symmetric. It does maybe look like they could be normally distributed, but we'll actually be able to run a statistical test. And I'll show you that when we build a different model a little bit later. But we could do that now. And of course, if we wanted our summary, 6-number summary of the residual distribution, we could run that. And we can see here the 6-number summary, our mean residual, as we know, had to be 0. And the median, we saw this earlier, was 20.19. And we get some dispersion as well that we can see from this summary. Now, let's take a look at answering some questions. There's a question in line number 67 here. It says, how does running a promotion affect sales on a given day? So let's go ahead and think about how we can answer that question. Let's do this by generating a plot of sales versus ad spend, but let's color it by the promotion variable. Okay, so we're going to create this plot here, and I'm going to use that same plot function, but we're going to feed it an extra piece of information. And what this is saying here is we're going to color the plot using a factor. We're going to convert promo, which is currently a numerical value, even though it's only binary. We're going to convert it to a factor, a categorical value, and we're going to color the data points by that particular variable. Okay, we're going to color them by promo, and when I run this plot here, and you'll see in the right diagram now, we are getting data points that have 2 different colors, right? There are red dots, there are blue dots. And if you look, it seems like the red dots are kind of bunched up and to the right, maybe suggesting that when you run the promotion, okay, these are associated with high ad spend, high sales days. So at kind of a first look, it does seem like the promotion maybe is associated with higher sales, but the question asked really, does it affect sales? And we're not entirely sure here because we know ad spend also potentially influences sales through this diagram. We can also add a legend to the plot if we want to. Okay, so if I run line 72 here, it'll actually run all the subsequent lines underneath it. So I'm using the legend function. I'm telling you, put it in the top left corner. I'm labeling the data points as promotion versus no promotion. I'm telling it to use red and black. And there are a couple other things, the shapes of the data points, the legend, how big you want the length and the width of the legend box to be, and the color of the legend box. So this is for aesthetics, right? We can add that legend there. It makes the diagram look a little bit nicer. But let's go ahead and build another model here that looks specifically only at how sales fluctuates with the promotion variable. We'll call this model M2. And this is the model we're going to build, where we have sales on the left. We're going to have promo on the right. And remember, promo is a type of dummy variable. It's either 0 or 1. So let's go ahead and estimate this particular model here, where we have sales, an intercept term, a slope, and only promo as the x variable. So we'll build that model, and we'll be able to see it pop up in our global environment in the top right here. Right, there it is. There's M2. And let's take a look at the summary output for M2. Okay, that model we just built, right? This model here. We'll take a look at that summary output down in the console window by running line 85. And here we go. Okay, again, some important pieces of information to look at here. Okay, regarding the this particular regression, we had the y variable was sales, the only x variable was promo. Okay, again, we're given some information on the residual distribution, but the most important place for us to look in terms of model diagnostics is here. Here we see that the intercept term is about 50,000. Which tells us that if we don't run a promotion, if promotion is equal to 0, okay, like we plug in a 0 for the promotion variable up in our regression. Right, here was the equation. We're plugging in a 0 for promotion into the regression. We didn't run one. Okay, what are we going to get? Well, we're going to get just B0 along the regression line there in terms of the fitted value. And that's what that intercept term is, right? If we don't run a promotion, on average, we're going to sell about 50,000 units. Okay, but our intercept term tells us when we do run a promotion, when promotion goes up by 1 unit from 0 to 1, it looks like that adds about 7,700 extra units of sales on a given day. And note, we do have very significant p-values, right? We see those 3 stars showing up. We have significance at the 0.001 level of alpha, at the 0.1% level of significance. You'll notice the R-squared is pretty low here. Okay, promotions only account for about 10% of fluctuation in sales from day to day in this model. And the model is jointly significant, right? The F-test, we get a p-value there. Again, very, very close to 0, definitely smaller than 5%, definitely smaller than 0.1%. So does promotion seem to affect sales? Again, it does, but we've only built this model with promotion as the X variable. We haven't yet tried to control also for ad spending at the same time, which we know is positively associated with the degree of sales. So the next question we're going to ask ourselves is, if we controlled for targeted ad spending, is the promotion actually effective? And it looks like promotions cause sales to go up, ad spending cause sales to go up, but promotion and ad spending could be correlated to each other, and they may interact. So let's go ahead and build a third model here. We'll call it model 3. And the model we're going to build now is going to have 2 parameters for us to estimate. We're going to have B0, B1, and B2. So we have an intercept and 2 slope terms. Since we now have, in this regression equation here, we have 2 variables that we are controlling for. We got our ad spend variable here. We got the promo variable here. We're controlling for both now. Those are both control variables or regressors. So let's go ahead and build model M3. And again, we will take a look at the summary output in the console window below. To do that, again, we go up here. Here's the model that we built. Okay, we can see the function. Whoop, let me scroll down there. We can see our function call, right? There's the model. We had sales on the left, ad spend and promo were the 2 variables on the right. And you'll notice the way that we add another variable is we just use a plus on the right-hand side of that tilde. We've add spend, and we've added the promotion variable here. So fairly, I think, simple syntax. We run that summary function to generate, again, this entire output down in the console window. And now there are some important things to take note of that are, I think, much different. You'll notice the coefficient on promotion has changed. It now says running a promotion, once we control for ad spend, it looks like running the promotion actually reduces sales. Okay? And that's not good. That might be some evidence that the promotion is actually doing exactly the opposite of what we want to do. But fortunately for us, we note that when we have ad spend in this regression, right, there is the ad spend variable, right? We have two variables on the right side. You'll notice promotion is no longer statistically significant once we've controlled for ad spend. The p-value is up at 35%, definitely bigger than 5% if that was our requisite level of significance, but we see no stars, no dots next to it. Okay, if it was significant between the 5 and 1% level, we would see this little dot next to it, and we don't even see that. Okay, so that tells us promo is statistically insignificant here. So we might want to think about eliminating that if we're just trying to predict sales using ad spending alone. That may be enough for us to have a reasonably good predictive model. The other thing you should note is the R squared here is a little bit higher than it was in the first model where all we controlled for was ad spending. I think it was just a little bit higher, up at about 54%. And again, this model is jointly significant despite the fact that the promotion variable does not seem to be individually significant here. And note the coefficient on ad spend, pretty close to what we got before, right? If ad spend goes up by 1, it's predicting about a 19 unit increase in sales, which was very similar. I think it was 18.85 when we had ad spend in our model, but we did not try to control for the promotion on the right-hand side. So the conclusion at this point is really to the extent that whether or not promotion is significantly helping sales, it does not really seem to once we have controlled for ad spending as well on the right-hand side. Now, what we're going to do next is we're going to build another model here, model 4, where we're going to add in impressions as well, social media impressions on the right. So now we're including 3 independent variables on the right, which means we're going to have to estimate 4 different parameters. We're going to have a beta 0, beta 1, beta 2, and beta 3 in this case. And this is a more complicated model. And the question is, does the more complicated model, does adding this extra feature, impressions, does it provide us enough extra explanatory power to offset the added complexity in the model, which means we may not generalize as well when we try to predict out of sample? And to think about that, remember a nice metric to be able to utilize here is the adjusted R squared. Okay, and that is the adjusted R squared on model 3 was 53.72. We're going to compare that to the adjusted R squared in model 4 because we know anytime you add a variable, it generally causes the multiple R squared to go up. Okay, or worst case, it stays the same. But the adjusted R squared includes this penalty for model complexity, meaning that could go up or down. Okay, it's going to go up if the explanatory power dominates the added model complexity. Okay, and that will happen if the t-statistic on this impressions variable is actually bigger than 1. That will cause the adjusted R squared to go up. Okay, but if it's not, right, if the extra explanatory power does not trump the added penalty for a loss of degree of freedom due to increased model complexity, then when we build this model M4 and we check the adjusted R squared, we might see that it goes down. So let's do that. Remembering the value of R squared that we want to compare it to here, let's just write it over here. It was 50.5372. That was the adjusted R squared value from model 3. So let's go ahead, let's build model 4, okay, where we also include impressions. We'll run that summary function for model 4. And take a look at what happened. Okay, it looks like the R squared, stayed about the same. It went up a little bit. Okay, but more importantly, the adjusted R squared, it did not go up. It actually went down. Okay, and you'll notice the t statistic on the new variable we added. We added impressions here. Okay, so a few things to see, right? The t statistic on impressions is definitely smaller than 1 in magnitude. So it did not provide us enough explanatory power to offset the added model complexity, which is why the R squared went down here relative to the value that we had in model 3. Okay, we also see impressions is definitely not significant. Promotions is still not significant in the presence of ad spending. Okay, and we're getting some values for the coefficients that don't really make sense. It says the more social media impressions we have, the lower the sales would be. So probably we want to remove promotion and impressions from the model here, despite the fact, again, that the F test tells us these variables are jointly significant. Okay, we've got a real low p-value on that F test. So let's go ahead and shift gears a little bit here. We thought about comparing two models, right, by adding another variable. Check the significance. We looked at the adjusted R squared, thought about goodness of fit. Again, the other metric you could look at is standard error here. It was 4948 on model 4. If we just go back up to model 3's output briefly here, so 0.4948, if we go up to model 3, 4941. So our residual standard error is even a little higher in model 4, 4941 up to 4948. Again, indicative that maybe model 4 is not as good of a candidate compared to model 3 in terms of fitting the data well. Moving on to this next question, are there seasonality effects related to a particular month or day of the week? So let's go ahead and build another model, M5, where we're going to control for now not only ad spending, but the month on the right-hand side. And you might remember the month is a qualitative variable, and what R automatically does is when you feed it a qualitative variable on the right-hand side, it automatically, and it won't show you this, this is going on underneath the hood, but it will create separate columns. It will create dummy variable columns for you, indicating if the month is January or not, or February or not. Okay, so on and so forth. So when we run this model, you're going to see that even though it looks like we added one variable on the right-hand side, when we look at the summary output, okay, from running model M5, okay, when we look at the summary output, okay, you'll notice down below, so let me just shrink this so you can see here. Okay, in terms of our coefficient estimates, we have several of them. There's quite a few, right? We have an intercept term, we have that ad spend coefficient, and then it looks like we have a coefficient for almost every month. But if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you'll notice one month is missing. Where is April? It's not there because April turns out to be built in to the intercept term. Okay. Now, the other thing to notice is when we controlled for seasonality, we see it looks like some months result in reductions in sales. Other months we have increases in sales predicted by whether or not it's that month or not, right? These are all dummy variables. So the way to interpret this value 330.5602 on May says that when we go from it not being May to being May, when we switch from April to May, that causes sales to go up by about 330 units on average, holding all the other factors fixed. But you'll notice here the p-value on that is huge. So none of these monthly effects here seem significant other than that intercept term. Okay, so that suggests we probably don't need to really control for all these months in thinking about seasonality effects. We can kind of not worry about the monthly effects here. So let's go back and let's check what about daily effects. Okay, so we're going to go ahead and build model 6 where instead of controlling for month on the right-hand side, we control for days. And let's go ahead and look at the summary output for model 6. And again, you'll notice when we're looking at that summary output here, our coefficient estimates, we get several of them. Okay, so we have our intercept, we have our coefficient on ad spend, right? Generally about the same size as it's been. Okay, note those things are significant, but the other thing that we see is also significant here okay, is we see that Saturday seems to have a significant effect on sales. Now, it's not very strong. It is down here between 1% and 5%. Sorry, it's between, it's between 1% and 5% level of significance. All right, and that should make sense because the p-value there is about 3%, 3.13%. So it looks like Saturday might be a significant day here in terms of seasonality effects. And we can see here that the model predicts that on Saturdays, we're actually selling about 2,000 units less than we would, not controlling for it being Saturday. You'll also notice we don't have a dummy for every single day of the week. It looks like we're missing Friday here, which is actually built into the intercept term. And the reason why we don't do that is because if we did, we run into a multi-collinearity problem where we know that the sum of the dummy variables for all the days has to equal 1. It's got to be at least one of those days. So in general, you don't want to fall into that dummy variable trap, that multi-collinearity trap, and R automatically kind of helps you out of that position. So it looks like Saturday is important. Looks like there wasn't too much of an importance effect with months in terms of seasonality, but let's suppose here we went with the whole shebang. What we're going to do here is we are going to build a model that regresses sales on all other variables except for the date variable. Okay, so the way we do that, we put a dot to tell it, want you to use all of the variables on the right-hand side, and then we use minus date to tell it to pull the date one out, except for the date. So we're going to go ahead and run model 7 here. And when we do that, we're going to get quite a few coefficient estimates. So let me go ahead and shrink the script screen in the top left and blow up the console window here. Okay, but here is the most complicated model. We've regressed sales on everything except for the date. So we have an intercept term. We have all these different dummies for days, right? Here are all of our day dummies. Okay, then we have a bunch of dummy variables controlling for months. Let's look at those. Clear that, redo that. So here were our day dummies. Okay, note that Saturday still looks to be like a significant feature, even though we've included all these other possible correlates. Here are our monthly effects, and notice the monthly effects don't seem to be significant at all, right, along the p-values there. Promo is still not significant. The price variable turns out not to be significant either. Ad spend is still highly significant, right, at the smaller than 0.001% level, a very, very tiny p-value. And impressions is still not significant either. Okay. Other thing we can recognize here is the R-squared must be pretty high for this model since we've made it very complicated. We've included a lot of information, and we were actually able to drive the R-squared in this model up to a value of 0.5606. But you'll notice our adjusted R-squared is much starts to actually drop relative to what we had seen before, where we had much simpler models. So we've included a lot of insignificant variables here. We've increased the model complexity by a whole lot, where a lot of variables were not worth the added complexity in terms of their explanatory power. And we can see with the F-test, we are dealing with some jointly significant model variables on the right-hand side. So that was us building a model using all of the variables in the data set with the exception of the date, which changes for every observation. Let's go ahead now and take a look at manually controlling for just Saturday. We saw the other days of the week weren't that interesting, but Saturday was. So what we're going to do here is we're going to add a new variable to the data frame. I'm going to add a variable called sat. And what we're going to do here is we're going to say, hey, we're going to look at the subset of the data frame where the day is equal to Saturday. And if it is, we are going to store the value 1 in there. So if it's Saturday, code the sat variable equal to 1. Otherwise, code the sat variable equal to 0. And this exclamation point equals is the logical expression for not equal to Saturday. So if we do this, and we view our data frame now, you'll notice, what do you see here? Well, in that far right column, we've added this Saturday variable, and it has a 1 showing up when it's actually Saturday, but when it's not Saturday, there's a 0 showing up in the case where it was Tuesday, right, or Monday. Okay, there's a 0 showing up. All right, so Saturday, when it's actually Saturday, we've created a dummy variable column here. And if we wanted to just check the effect of Saturday being statistically significant or not, we can now do that by building a regression. And in model 8, what we're going to do here is we're going to look at building a model where we've controlled for ad spending and only the Saturday effect. Okay, so let's go ahead and check that. And let's look at the summary of our model output here. Okay, so here is the model that we built. Here we got sales on the left, beta 0, beta 1, and beta 2 in front of Saturday. And if we look, we can see here that it looks like we got a pretty okay model. We see our significance codes. Each of these parameter estimates is significant. Our intercept, our ad spend, and our Saturday variable here says on Saturdays there is a seasonality effect that's significant at between the 5 and 1% level. And if on a Saturday, it looks like our sales decreased by 1,731 units-ish on average. Okay, here is our R-squared. So this model is capable of explaining about 55% of the variation in sales from day to day by controlling for ad spending and whether or not it is Saturday. And here is our adjusted R-squared, and we note the model is jointly significant. So this looks like a pretty good model here in terms of at least significance and fitting the data reasonably compared to some of the alternatives we've looked at. If we wanted to make a confidence interval table for our estimates, what we can do here is I'm going to use the cbind function, and I know I showed you how to build the confidence interval earlier. But the cbind function, what that does is it takes a column of information and it puts it next to another one. So we're going to put the coefficient values, which are these guys here. Okay, we're going to put those in a column right next to the confidence interval bounds. Okay, so let's go ahead and look at that. We're putting the coefficients next to the confidence interval bounds. We're C-binding them, we're column binding them. So when we run line 116 here, okay, we get a very nice organized confidence interval table down in the console window. Okay, we're in the first column, we have the center of the confidence interval. That is the actual coefficients in the first column. Here is the lower bound, and here is the upper bound in the third column. So we can see here, for example, if you look at the intercept term, we're at the confidence interval centered at about 12,872, but the lower bound goes down to about 9,174, all the way to the upper bound of about 16,571. Right, so again, pretty easy here in R to build that model, boom, immediately get your confidence intervals associated with those parameter estimates, with those beta values. We're going to do a little bit more detailed residual analysis for model 8 here than we had done before. So we saw we could plot them as a scatter plot. There's the AB line at 0. And again, it doesn't look like we have heteroscedastic errors. What I mean by that is it seems like the error variance stays fairly constant within these horizontal error bands. It seems pretty constant in terms of the residual error. So it looks like we are dealing with a fairly homoscedastic situation. Let's go ahead and add a histogram plot to look at the distribution of these residuals. And they look nice and bell-shaped. If we wanted to overlay that normal density curve, we could. They look fairly normally distributed here, and we could generate some summary statistics, that 6-number summary for those residuals. Note that there is some skewness. The median is different than the mean residual here. And that might mean that they're not normally distributed. But what we're going to do next is I'm going to load a library called T-Series. And you may need to first install the T-Series package to do this. So if you, in the bottom right, you click on Packages, you click on the Install button. If you type T-Series, You'll see it comes up there. You click that, you hit install, install the dependencies as well, and you should be good to go. But let's load up this library. And what we're going to do here is we're going to conduct a hypothesis test for normality called the Jark-Barrett test. This is a parametric statistical test that checks the skewness of the distribution in the data against the skewness for a normal distribution, which is 0. And it also checks the kurtosis, how fat the tails are in the data, compared to how fat the tails are in a normal distribution. So when we run the Jark-Barrett test function on our residuals, okay, it's going to report to us the results of that statistical test where, again, the null hypothesis is that the data is normally distributed, and the alternative hypothesis is that the data are not normally distributed. So when we run that test, okay, you'll notice the results popped up down in the console window here. Okay, they give us the test statistic, and this is actually, they're using something called a chi-square distribution for the test statistic. So if you had a table for the chi-square distribution, you could check at what significance level does that give us a significance result. But the, again, nice thing about most statistical software packages is they show you the p-value. And here we see that that p-value is pretty big, 38.13%, which means we absolutely cannot reject the null hypothesis that the residuals are normally distributed here. Okay, we cannot reject the null hypothesis that the residuals in our data are normally distributed in that plot that we were looking at. So that is one way you can think about testing a set of data to see if it is actually normally distributed. You can use this Jark-Barrett test. The other thing I would like to wrap up with is just show you very quickly how to use the partitioning of the data into a training and testing set in order to calculate your out-of-sample performance and to actually make predictions out of sample on new data points that you did not use to build the model. So what we're going to do here is I'm going to take the data and I'm going to break it up into 2 subsets. It turns out with time series data, when you set aside some data to test with, you have to do this keeping in mind there's chronology in the data set. So what we're going to do, given that we have 12 months of data, is I'm going to build the model using the data from every month except for December. Okay, so we're going to take a subset of our data frame, DF, and we're telling it we're going to take the subset of the data frame where the month is not equal to December, and that will give us what we're going to call the training data set. Okay, and you'll notice the training data set, if you look in the top right in that global environment window, we have 334 observations now. We did not include the 31 days of December, which would have added up to 365. Our testing data set, we are going to take the subset of the original data frame where the month is equal to December. Okay, and we can see here the testing set in the top right global environment window has 31 observations. Those are our 31 days in December. Okay. And if we wanted to just verify that we had partitioned properly, we can check the dimensions of the training data. We have 9 variables. Remember, we added that Saturday dummy variable in there, which is why we have 9 instead of 8. And there are 334 days in the training data. In the testing data, when we run line 140, we have 31 observations. Those are the 31 days in December for those 9 variables. And if we view the testing data, here's what the testing data looks like. You'll notice if you look down the month column here, right, we are only dealing with the month of December. Okay, and we are not starting with observation 1. We're starting with observation 335. All right, so this is what our testing partition looks like. So what we're going to do next is something known as model validation. We're going to estimate our out-of-sample performance by essentially hiding the testing data. Okay, we're going to build the model from only those first 11 months training data. And then when we want to check how well the model does, we're going to pull out the month of December and use that to benchmark the model's performance. Okay, that way we can make sure we didn't just memorize the data. Right, we hid some of it away, we hid December, so that'll give us a little bit more honest estimate of our out-of-sample performance. Okay, so let's go ahead, we're gonna rebuild model 8. Okay, but we're gonna only use the training data to do that here. So I'm feeding it only the training data. So it's the same structure of the model in model 8. We have add spend in that Saturday dummy variable on the right, but I'm building it with different data, which means the parameter estimates we're going to get when we look at the summary, they will be a little bit different. Okay, note that we're still getting some nice significant results. Okay, our parameter estimates in terms of our betas, they are all significant. Okay, the sign on Saturday stayed the same, ad spend's about where we expected it to be, and that intercept's about where we expected it to be. Okay, we're still explaining about 55% of the variation in sales from day to day by including ad spend in that Saturday dummy, and we have jointly significant results, okay, according to the F-test here. Note our residual standard errors at 4,859. That is our measure of in-sample error. That's our EN for this model. What we will want to do is compare that number, 4,859, to how we would actually perform on the December values, right, out of sample data. So we could go ahead and just remember this value here. We had EN was equal to 4,859. And remember, our in-sample error, this is always a little bit biased, right, in that it makes us look a little better. It's a little bit lower than probably what our actual error is, since we used the sample data to build the model. We've memorized that data already. So if we test ourselves using what we memorized, of course we're going to do good on it. But we will keep that value referenced here momentarily. So let me clear these up. And let's go ahead now and generate model predictions. So what we're going to do now is we are going to evaluate model 9, but we're going to evaluate it by plugging in the testing data, the December observations, to formulate predictions. So in line 148 here, we're going to use the predict function. We're going to feed it two things. We're feeding it the model that we want to predict, which is M9. That's the model we built with the training data. And we're going to feed it the testing data now. So we're using the model we trained with the training data, but we're going to feed it the testing data to generate predictions for the month of December based on our model estimates here. And we can go ahead and view these predictions. So let's generate them, and then let's view them. Okay, so here is the prediction for December 1st. That was observation 335 in the testing data, right? There. So we got now an entire vector of our predictions from days 335 to 365. That is the month of December. And what we can do now is we can calculate the root mean square error prediction, the mean square prediction error, the root mean square error on the test data, which is really our measure of what we're calling E out, the out of sample error. Again, let's remember we had an in-sample error of 4,859. So if we had calculated our out-of-sample prediction error here, okay, what we're doing, well, let's just look at this line 152 carefully. We're measuring how far the prediction is from the actual value in the test data. So that's the actual value of sales on a day in December. We're measuring how far is the predicted value from that, and then we're squaring it. So there's our squared deviation, okay, comparing the predicted value to the actual value. Then we're summing them up. So we're adding the square deviations, and then we're dividing by n, but we have a -3 adjustment here for degrees of freedom, n -3, since we had to estimate 3 model parameters, right? We estimated 3 parameters, so our degrees of freedom adjustment is n -3 in that case. And if we go ahead and run line 152, which calculates the average prediction error. Also note, we're taking the square root of it at the very end here. We're taking the square root of the sum of the squared prediction error, right? Really the average prediction error divided by n minus that degrees of freedom adjustment over here, right? Length of testing, length of that data set is the number of observations in that data set. Okay, -3, that degrees of freedom adjustment. And when we run line 152, it will compute the mean square error. And if we actually report it, you'll notice we're getting an E out value here that is, as we suspected, bigger than E in. So this is our estimated value of our prediction error in really an honest sense. We're using data that we didn't use to build the model to actually evaluate the model here. Okay, so our E out, what is that going to be? It is 5713.693, which is definitely bigger than E in, as we expect. Generally, this is true on average, but sometimes you never know. You could get a test data set that happens to, your model fits it really, really well compared to your in-sample data. Weird things can happen sometimes. But that is where I would like to wrap up. So we did a lot of linear model building here. We did some exploratory analysis, we built some visualizations to help us out. We answered some questions about the actual data set and some relationships in the data set. We thought about interpreting diagnostic model results, and then we did some actual out-of-sample prediction by partitioning the data into training and test sets, and evaluating the efficacy of that model by computing this out-of-sample error metric. If we had to compare models in terms of how good we are at predicting, I would really use that E out metric as kind of your guiding light. That tells you how good you are at predicting relative to the true population function, that true data generating process. So hope that was useful. Stay tuned.